Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello students, let us discuss about the applications of conservation of angular momentum. So students, let us start with the application part of the conservation of angular momentum. In short, you can say it is CAP, conservation of angular momentum. So we are talking about the application. Application number 1. In case of ice skater delight, we have seen that in ice when the dancer who performs on ice when when it rotates or spins about its axis, so there is angular velocity, and this person who is spinning about its axis, if it wants to increase the speed or decrease the speed, that is the rotational speed, what it should do? We have seen that this is based on CAM, how that we'll discuss. It can, we have two diagrams I'll make here. One is that when he or she folds the arms, and in this position he outstretches the arms, open the arms apart. Here it brings the arms more closer to the body. So in these two situations, now you guess, suppose this is omega 1, suppose this is omega 2, in which case you think that the omega is more. To understand that, let us understand what is conservation angular momentum that we discussed. The formula is I omega. This is based on conservation, that means this is constant. In this system, there is no external torque acting. So I omega has to be constant. When I omega is constant, then by variation of I, if I change I, suppose I increase the I value, then this value has to be decreased, because if one increases, the other has to decrease, so that the number product is constant. If I decrease the I value, omega has to increase. That means we have to see, to check whether the omega is more or less or more, we have to see if I is more or less. And the moment of inertia is a quantity which depends on axis of rotation and the distribution of mass. In this diagram, first diagram, and this is suppose the second diagram, in the first diagram the arms are away from the axis of rotation. Here the arms are folded and more closer to the axis of rotation. In this situation, in this scenario, the distribution of mass is farther away from the axis of rotation. In this situation, the masses are more closer to the axis of rotation. If the distribution of masses are nearer, then the I value is less. So here the I2 value is less, and here the I1 value is more. When the masses are distributed away and away from the axis of rotation, we know that the R value will increase and then mR square value will increase. So if I increases, omega has to decrease. So this has to be decreased. Here the I2 is less, so omega will increase. That means in case of a eye scattered daylight, when the speed rotation is more, when it is required that the speed should be more, they bring the hands closer to the axis of rotation. They bring their arms very close to, or fold their arms. By folding the arms, the speed will increase, and by opening the arms, suddenly the speed will decrease. So this is how it is done, but the product is always constant. So in this situation, I can write I1 omega 1 is always equal to I2 omega 2. I'll just give a number to make it understand. Suppose that I'll arbitrarily take this value is suppose 10 and this value is suppose 2. Suppose this is 2 and this is 10. I omega, I say it is 20 in 20, and in this situation, suppose that this is 10 and this is 2, so 10 into 2 is 20. Now, in this situation, when you fold the arms, then I will decrease. Suppose that it decreases from 10 to suppose 5. If this is 5, how much I require to make 20? I require 4. Again, because this decreases, so 5 into 4. 5 4s are 20 and 10 2s are also 20. What is happening? If you see that the omega 1 here is 2, now it is 4. It's increasing. That already we discussed that if one decreases, the other has to increase to compensate so that the product remains constant. This is one application. Another application is like when you suppose someone is sitting on a rotating chair. There is a rotating chair. You just sit there and tell somebody to just give you a little pull so that you can rotate. When you start rotating, just then you open the arms, the speed will decrease suddenly. And again you fold the arms, speed will increase. Again open the arms, speed will decrease. So this situation and that situation is same. You will feel that yourself that when you fold your arms, your speed omega will increase. When you put your arms out, then the speed will decrease. This is one application. Now let us discuss another type of application, that is application number 2. We'll take another situation where the angular momentum is also conserved. Suppose that I have wheels rotating. There is one wheel here. Over this axis obviously is rotating over this axis. This is a wheel. This is a wheel which is rotating. Okay, with omega. It's rotating and or suppose I say it is omega 1. The wheel is having moment of inertia over this axis, suppose I1. There might be similar wheel or any other type of wheel which is rotating somewhere here. There is another wheel here. It's rotating on its own way with another angular velocity omega 2 and the axis of rotation. For this axis of rotation, this I is suppose I2. So there are two wheels rotating. They might be in the same axis or might be in different axis, no problem with that. Now its angular momentum is I1 omega 1 because angular momentum is I omega. And this for second wheel, the angular, this is the first wheel and this is the second wheel, or I'll name it as A and B. So the wheel A is having angular momentum I1 omega 1 and the second wheel is having angular momentum I2 omega 2. Now if I take this wheel or slightly make this wheel move slowly towards the first wheel A and gently place them together, connect them, then there will be, so when they are stuck together, when you stick them together, then it might be rotating with another omega, it might be rotating with another omega. So they might have a different omega, but suppose it's moving with frequency, suppose 100 rpm, and the other one is suppose moving with 120 rpm. When they are put together, they're made to rotate as a single disk. Then this omega will change, or the frequency will change, and it will have some other frequency which is a common frequency, common omega, with both. Now it was moving with certain omega, it is certain omega. Now when they are put together, one is moving faster, one is moving slower, suppose like this. Together, then they move with certain another omega. In this situation, when they are placed together, the diagram is something like that. That one well and there is another well connected together. Okay, and when they are connected together, they will have a common omega. I don't know that value, that we are going to find omega. Moment of inertia will not change because moment of inertia is independent of whether it is omega 1, omega 2 or omega. It depends only about the axis, because I have not changed the axis. It is the same axis only that I kept. The axis is passing through center and perpendicular to the plane of the wheel, like that. So in this case, still the moment of inertia will remain the same, I1, and here also it is I2. Because I have gently placed, so I have not externally added any torque to the system. This is my system consisting of two wheels, and because there is no external torque, so angular momentum will remain conserved. How to conserve that? This is the initial situation, initial condition, initial state, and this is the final state. So I'll just find the angular momentum of the system before they are together and after they are together. So in the first case, in the initial state, the angular momentum will be L1 plus L2 is the angular momentum for this is before, that will be before, and after suppose L, so it is after. Now I can just equate them because how can I write this one is equal to this one, because net external torque is 0. So L1 is obviously I1 omega 1 and L2 is I2 omega 2, which is equal to I is now, when both are together, so I1 and I2 will be the moment of inertia of the system. So they have to be there to add it. And suppose they're moving with common omega. So from here, omega I can write as I1 omega 1 plus I2 omega 2 over I1 plus I2. This is the situation when they're together. This is the omega with which the two wheels will rotate with common omega, that is this one. This is how you find this. So you can have one more applications also, but it's not required. It is two applications enough. There might be many various situations where you can apply conservation of angular momentum. For example, a disk is rotating, okay, and another piece of object is dropped, like wax is dropped, and falls down and sticks to some place of this disk, then that stick to it, and now the system consisting of the disk and the wax will rotate together. So this is the situation when there is like the common omega. In this situation also you can use this equation, but then you have to keep in mind that the omega here individually you have to find what is the angular momentum of the system of the disk and the wax before and after that together, and what is the angular momentum. So we can also discuss that part also. Let us discuss that if you want. Then suppose this is application 3. What is that part? I'm talking about a disk. There is a disk plus wax system. Wax is here. It is allowed to fall down and it sticks to this place. This is the situation before and just before hitting it might have certain velocity, but then we'll neglect the velocity because we consider that this is not going to have external torque by falling, because when it hits then it gives a force and that will create a torque, and that torque will I can also consider the torque is the internal, because I have considered this particle and this object as system. Now in this situation I can apply again conservation of angular momentum, but in this situation I will consider that m is the mass of the disk, which is rotating with angular velocity omega and radius is r. And this situation, this mass is, suppose this is a small mass m, falls down from a gently placed, or you can see gently placed here, so there is no torque due to that. This is distance, the radius of this is r, but the point where it sticks and then starts rotating with a common omega, after it will sticking here, the omega with it they will rotate is suppose omega, before sticking it is rotating with omega 1. So in this situation I can always write the equation like before this wax falls down, the angular momentum of the system was, its angular momentum is I1 omega 1, and here the angular momentum can be considered to be mvr, because depending on what height it is released and how much velocity it will gain when sticking, that is the velocity under 2gh. If it is released from height h, then the velocity here while striking will be 2gh under root. So I know the velocity which will hit the object, and I can find mv, momentum in the direction r, so it is mvr, that is m small m under root 2gh, and this distance x or r, whatever you take. Suppose this distance is x from here to the point where the wax is stopped. Now before and after that, the moment of inertia due to this disk is suppose I1, and that will be there, and also along with this we have the moment of inertia of this small wax, which is mx square. So this is mx square. This is the total moment of inertia of the system, and that rotates with omega. This is the final angular momentum of the system. Initially it was suppose I1 omega 1. You can consider this one, or you may not consider. In most of the books they don't consider because they don't take the height also, because you take the height then you get the velocity, then you get m small m v is 2g as under root and r is suppose x, then this is the angular momentum. This has to be added with this. If I do that, then it will be I1 omega 1 plus m of under root 2gh to x because mvr, and that is equal to the total conservation of angular momentum, that comes to be I1 mx square into omega. So generally this part is neglected in most of the books. So only I1 omega is this. From here omega I will get. If I make this 0, then omega will be I1 omega 1 divided by I1 plus mx square. So that equation you can use. Okay, that's all about your applications. Thank you.